Hi everyone. Today we are discussing the first exercise of first chapter, exercise 1.1 of NCERT Mathematics textbook. Here is our first question. Use Euclid's division algorithm to find HCF of 135 and 225. So here two numbers are given, 135 and 225. Yes, let's try to find the HCF using Euclid's division algorithm. So as we know, the Euclid's division algorithm for any two number a and b, we can find q and r such that a can be written as bq plus r. Such kind of q and r we can find out for this a and b. Here a and b are 135 and 225. Let's take the largest number as a and the smallest number as b. That is 135 is b. 135 is b and 225 is a. Okay, so that let's divide 225 with the 135, so that we will get 1 as the quotient. Let's divide 225 divided by 135. You will get 1, and 135 is there, and remaining is, we know, that is 0, 9. Okay, so 90 is the remainder here, so that we can write 225 is equal to 1 times 135 plus 90. Now in second step, we are taking this 90 as our divisor and 135 as the dividend. Okay, so that we can write 135 is equal to which number into 90? How many 90s are there in 135? Actually, no need to divide all these times. This thing we can do in our mind. Now we are thinking how many 90s there. Obviously, we know only one 90 is there in 135. So then here also we can write 1 times 90, and the remaining is 90 plus 1 times 90 is 90. 90 plus 45 you will get 135. So 45 is the remainder here. Next step, we are taking 90 as dividend and 45 as divisor. So that we can write 90 is equal to 2 times 45. Now exactly 2 45s will contain in 90. So nothing will remain. The remainder is 0. So here we can see that the last non-zero remainder is 45, or the last divisor or last non-zero remainder. That is the HCF. So that we can write the answer as HCF is equal to 45. Now let's consider the second question. Second question is saying use Euclid's division algorithm to find HCF of 196 and 38,220. For finding the HCF of these two numbers using Euclid's division algorithm, let's take the largest number as A and smallest number as B. And we can write 38,220. Let's try to represent this number 38,220 in the form of BQ plus R, where B is 196. So that we are trying to divide this number 38,220 with 196. So if you try dividing this, you will get 195. 196 times 195. You will get this number 38,220, and the remainder is 0. So in the first multiplication itself, first time itself, you will get remainder 0. The first remainder itself is 0. So we are taking the last divisor. That is, the divisor here is 196 itself. So 196 itself is the HCF of these two numbers. HCF of 196 and 38,220 is equal to 196. Let's move to next question. Here is the next question. Show that any positive odd integer is of the form 6 cube plus 1 or 6 cube plus 3 or 6 cube plus 5 where q is some integer. So here we have to find or we have to show that any positive integer is of the form any of these. Positive, not positive integer, positive odd integer. Any positive odd integer is of the form is any of this form. Okay, and q can be in some integer. Okay, let's try to apply Euclid's division lemma here. We shall take b as 6 so that we can write any positive integer in the form of a is equal to bq plus r. If you are taking b as 6, we are taking b as 6 and let a be any positive integer and b be 6. So that we will get the answer a is equal to 6 cube plus r. The range of this remainder r will be ranging from 0, 0 less than or equal to r less than b. Here b is 6. So that the possible value of r, the remainder r will be either 0, 1, 2, 3, 4, less than 6 means up to 5. 0 to 5. These are the possible values of r. Now let's try to list out all the possible forms of the any real number, any positive odd integer a. So here we will get a is equal to, when r is equal to 0, that will be 6 cube. When r is equal to 1, that will become 6 cube plus 1. When r is equal to 2, that will become 6 cube plus 2. When r is equal to 3, that will become 6 cube plus 3. Like that. When r is equal to 5, it will become 6 cube plus 5. These are the possible forms of any positive integer. Okay. Now let's see which are odd among them and which are even among them. Let's check the first one. First one is a is equal to 6 cube. A is equal to 6 cube can be, we can take 2 outside. 2 into 3 cube. We can write this a as, in first case we can write it as a is equal to 2 into 3 cube, some value, 2 into some integer. So this is even. In second case we cannot take 2 outside, so this is odd value. This will be odd. And in third case we can write this as a is equal to 2 into 3 cube plus 1. So this is also a form of 2 into some integer. So this is even. And third case, next case, or third case, this is next, fourth case. 6 cube plus 3. Here also we cannot take 2 outside, 2 common outside. So that this also will be odd. This also will be an odd value. And in next case, we can see that 6 cube plus 4. There also we can write, I have left that anyway, that you can written as a is equal to 2 into 3 cube plus 2. That's only. So that will be even. Now this will be 6 cube plus 5. Here also you cannot take 2 outside. So this also will be odd. So the all the odd integers will be of the form given here are 6 cube plus 1 is odd number, 6 cube plus 3 is odd number, and 6 cube plus 5 is odd number. In all other case, you can write a as 2 into some integer. Here also 2 into some integer. Here also 2 into some integer. So that these all are even values, but here you will get odd values. 6 cube plus 1, 6 cube plus 3, and 6 cube plus 5. These are the only odd values. So that we can say that any positive odd integer can be written in the form of, any positive odd integer can be written in the form of any one among them. 6 cube plus 1, 6 cube plus 3, or 6 cube plus 5. Hence the answer. Now let's come to next question. This is a bad problem. An army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? This is the question. Let's see. Let's analyze the question. Here there is an army contingent of 616 members. 616 members of army is there. So they have to arrange for a parade. 616 members like this. They have to arrange. Okay. So like this, they are standing in rows and columns. Then another thing is that they have to arrange behind a band of 32 members in a parade. So in front of them, they have to arrange 32 members in front of them. So these are the band members. I am marking them in red color. So these are band members. There are 32 members are there. So these are band. These are band members. Behind this band members, here is army. And they have to arrange it for their parade in this manner. So number of columns should be equal. Number of columns should be equal so that they can stand in a parade like this manner. So we want to find what is the maximum number of columns in which they can march. If they want to arrange it in such a manner, then what is the maximum number of columns? Maximum number. We know that number of columns here is the factor of total number of band members. And same manner, the number of columns will be a factor of army members as well. So this number of columns will be, the number of columns will be common factor of this number of band members as well as number of army members. So the maximum possible such a number is maximum common factor or the highest common factor. That is the maximum number of possible columns. From here this contest, this is clear that we have to find HCF of these two numbers. Here the question is to find HCF of 616 and 32. Let's find the HCF of 616 and 32 using Euclid's division lemma. Okay, I am applying the Euclid's division algorithm here. I am dividing 616 with 32. I will get 1 times 32 is there and remaining is 29, 296 and 9 times 32 contains in 296, that is 288 and remaining is 8. Now next step, I am making this 8 as divisor, the remainder as divisor and dividing again with 32. I am dividing with 32 and I will get 4 times 8 is 32 and the remainder is 0. So when I am getting 0, I can stop it here and I can see that 8 is the last divisor. Last divisor is the last non-zero remainder, that is HCF. So that we will get HCF of 32 and 616 is equal to 8. So that they can have 8 columns in the parade. Here is the next question. Next question shows that use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. So any number, for any number, square of it is of the form 3m or 3m plus 1 for some integer m. Okay, let's think about the square of a number. Before thinking about the square of a number, let's think about a number a. If I am dividing a using the integer 3, I will get A in the form of 3q or 3q plus 1 or 3q plus 2. So any positive integer I can return in the form of 3q, 3q plus 1 or 3q plus 2. Since a can be written as 3q or 3q plus 1 or 3q plus 2, let's think about a square. What about a square? A square can be written as the whole square of 3q whole square, which is equal to 9q square. This 9q square can be written as some 3 into 3q square. This can be written as 3 into m because we are taking m as 3q square. Next, we are taking the second case. If a square is of the form of 3q plus 1, let's take a square in second case. This is case 1. Case 1 means a is equal to 3q. Then next, second, we are considering case 2. Second is case 2. Case 2 means a is equal to 3q plus 1. That is case 2. When a is equal to 3q plus 1, a square is equal to 3q plus 1 whole square. So using a plus b whole square, we can expand this. 3q whole square means 9q square, that is a square. A square plus 2 times ab, 2 times 3q into 1 plus b square is 1 square. Now I am simplifying this. I will get 9q square plus 2 times 3 is 6. 6q into 1 plus 1. Now I can take this 9q square and 6q together and taking 3 outside, so that I can write this as 3 times 3q square plus 2q plus 1. Here in this second case, I can take this 3q square plus 2q as m, so that I can write this as 3m plus 1, where m is equal to 3q square plus 2q. Now let's consider case 3. This is case 3. In case 3, we are considering a as 3q plus 2. Then a square will become a square is equal to 3q plus 2 whole square. Here also we can expand this using a plus b whole square. A square 3q square. Okay, I shall write this as 9q square. A square plus 2 times 3q plus 3q into 2. 2 times 3q into 2 plus b square is equal to 2 square. Now I am simplifying this term. I will get 9q square plus 12q plus 4. Here also usually I want to take 3 outside, but in all these 2 times 3 is available to take outside. So in the third time I cannot take 3 outside. I want to come to the form of 3m plus 1. So that I'm doing a small rearrangement here. I am rewriting this as 9q square plus 12q plus 3 plus 1. I'm writing this 4 as 3 plus 1. And next step, I am taking this, taking first 3 times and taking 3 outside. I will get 3 into 3q square plus 4q plus 1, and in a bracket, I'm closing the bracket and putting 1 outside plus 1, and same thing I can written as 3m plus 1. where here we know m is this quantity. This quantity I am writing as m, where m is equal to 3q plus 3q square plus 4q plus 1. Let's consider next question. Next question is given as use Euclid's division lemma to show that the cube of any positive integer is either of the form 9m, 9m plus 1 or 9n plus 8. Here also we are applying the same technique we have used in our previous question. First of all, we are taking any integer a as 3q plus 3q or 3q plus 1 or 3q plus 2, and we are considering this as three different cases. Let's take the first case and we shall take the cube. In first case, we shall take the cube. Here a cube is equal to 3q all cube, that is equal to 27 cube, 27 cube. And the same thing we can take in the same time we can take 9 outside, 9 times 3q cube, and that can be written as 9 times m, where m is equal to this thing, that is 3q cube. So this is the first case. Let's consider the second case. Case 2, a is equal to 3q plus 1. Then a cube will be equal to 3q plus 1 whole cube. And I am expanding this a plus b whole cube. A plus b whole cube, as all of you know, a plus b whole cube is equal to a cube plus 3a square b plus 3ab square plus b cube. This is expansion of a plus b whole cube. I am applying this here and I will get a plus b whole cube as a cube, that is 27q cube plus 3a square b, 3 into 9q square into b plus 3ab square, 3 into 3q plus b cube is equal to 1. Then I am simplifying these terms. I will get 27q cube plus 27q square plus 9q plus 1. Here from all these terms I can take 9 outside. I am taking 9 outside. I will get 9 times 3q cube plus 3q square plus q plus 1. And here I can take this as m. I can take this entire term as m, and I can write this as 9m plus 1, where we know that m is equal to 3q cube plus 3q square plus q. In last case, we are taking a as 3q plus 2. Then we will get a cube is equal to 3q plus 2 all cube. I am expanding this. I will get 27q plus 3a square b, 3a square b plus 3ab square, 3 into a into b square plus b cube is equal to 2 cube. Then this is equal to 27q plus, I am simplifying, 9 into 3 into 2, 54q q square plus 3 into 3 into 2 square, 36 cube plus 2 cube, 8. This is equal to, I'm taking 9 outside. 9 times 3 cube plus 6 q square plus 4 cube plus 8. And same thing I can written as 9m plus 8. Here m is equal to 9q plus 6q square plus 4q. That is the thing inside the bracket I'm taking as m that I have written here. So now the cube is of the form 9m plus 8. Hence the result.